So the first question was identify allylic or benzylic resonance structures. So maybe we'll do it first in the context of the radical stuff, and then we'll do it in the context of ionization, so carbocation formation. So let's look at allylic first. So allylic and benzylic are like, if I told you to go down to 4th Street and make a left. So it's sort of like, I don't know, a marker in a way. So an allylic system has a pi bond, then another carbon, and for this case, I'm just going to put a hydrogen. I'm specifying that hydrogen even though there's 3 on that carbon. So with the red dot here, that's the allylic carbon. So you have an alkene. It's an sp3 hybridized carbon that's bonded to it. That's what allylic means. So if we were to form an allylic radical, so I'm actually going to remove that dot so as to not confuse anyone. So if I just said form an allylic radical through homolytic cleavage. So homolytic means it's the same type, so it's radical. We use the fishhook arrow, which is a single-headed arrow, to note how those electrons are moving. So once we get here, now the carbon that started off as sp3 hybridized is now sp2 hybridized. It has a radical plus hydrogen. So what do we mean by resonance? And I'm going to use numbers in blue here to say that this carbon 1, 2, and 3, that the radical is going to migrate over to carbon 3. And so what does resonance really mean? So we use this double-headed arrow. That's a resonance hybrid. And both of those structures exist at the same time. It's like the same thing. So really what you want to think about it is carbons 1 and 3 both have radical character. They're not specifically radicals themselves, like just a radical. It's sort of both of them. You see carbon 2 always remains in the alkene, so it doesn't have that character. So you sort of differentiate amongst those 3 carbons that 1 and 3 are the reactive centers and 2 is not. So in an allylic system, you can show 2 distinct resonance hybrids. So benzylic is a little bit more complicated, but I think what you'll see is the allylic pattern exists in a benzylic system. So I'll use an arrow. And so that's the benzylic carbon. It's the sp3 hybridized carbon bonded to the ring. And what I want to draw your eye to is, so I'm going to use this laser pointer on this app here. See, in the allylic system, you have a pi bond, then you have this sigma bond with sp3 hybridized carbon. That allylic system is sort of embedded here in the benzylic, right? You can sort of see that 3-carbon unit. So I'm going to go ahead and draw the benzylic hydrogen in, and we'll show that cleaving homolytically. So we get a benzylic radical. Plus our proton. Hydrogen. So now you're going to do the same thing. you identify the first hybrid, so we could say 1, 2, 3. Then we're going to migrate that radical over to carbon 3. Then you're going to see that allylic system show up again over here. So this would be 1, 2, 3, 1, 2, 3, and then back out of the ring. So the benzylic is actually a little bit more stable because you have more places of which that radical is delocalized. And so these are just the fishhook arrows showing the movement. So I'm going to go this way. So the benzene has 4 resonance hybrids that we can think of. And again, you can't learn everything all at once. And so some of the things you learn now, we're not going to really revisit until 256. But the benzene resonance structures are pretty important when we start learning the reactions of benzene itself. So you can imagine, instead of having a radical, you have 2 electrons as a negative charge. That negative charge can move over. If you have a positive charge, the pi bond swings over itself. So of the reactive intermediates, you know radical, anion, carbocation. The concept is the same for delocalizing the charge.
So we just need to be able to look at a structure and know that there's resonance on it? Or like that the radical or the carbocation or whatever has resonance on there to know that it's more stable than something else?
Yes. So I have this book here. Let me put another example of allylic resonance in sort of a different context so that you can see it. Now within this structure here, are you able to see that this oxygen radical is allylic? So the oxygen has its 2 lone pairs, sigma bond now has a radical. The overall, so when I set up here, see how that allylic is sort of embedded here? Now if you think about it different, what's to say, why do all of these have to be carbon?
Okay.
So I put an oxygen, you have the pi bond, now here I have oxygen. So that's still an allylic resonance. So we can draw that as well with this fishhook notation. So I hope that's sort of getting at what you're asking about being able to look at something and determine if it's allylic or benzylic. You have a follow-up question?
Kind of, yeah. What, the rankings of tertiary, all that with benzylic, the methyl, and the allylic, all those in it? Would the benzene be more stable always? Or does it also flip depending on the mechanism?
It typically is, because what we mean by stability, like I said, a radical, a carbocation, and a carbanion. If you're thinking about that energy coordinate, time moving this way, and energy going up, wherever you start in the reactant, those things are always going to be higher. But in these systems where you can delocalize means you're stabilizing that, so it brings the energy a little bit down. This has more resonance forms, which means it's more stable. So hopefully that's a little bit clearer to you.
It helps. Yeah.
Do you have a question specifically? So let me pose a question to you, sort of see if you're understanding some of these concepts here. And this is straight out of another book. So this is classification of hydrogens. And this is a pretty important concept for the free radical CH substitutions. So say you're given this. This molecule is methyl cyclopentane. And I've asked you in lecture, so how many unique carbons, how many unique hydrogens? So let's focus specifically on the hydrogens and we'll sort of drill down. So in this molecule, how many unique sets of hydrogens do you see? We have 3, we have a 4. 4. What's your 4? So 4 is going to win. So we have this, these two are the same, those two are the same. So there's a mirror plane that gives it symmetry.
So we'll make a difference.
So that's what we're gonna go through now. So in red, what I'm gonna do here is just sort of capture this information because I want you to see how the logic can progress so that you arrive at the right answer. So we have 4 unique sets of hydrogen. I think we all can agree that every carbon is sp3 hybridized. So we're going to get into now classifying them. So let's look. We have primary, secondary, tertiary. So how many primary hydrogens are there? What's the number of primary? What? So 1 or 3. Whose explanation is going to win?
I think it's 1 because doesn't all hydrogen carbons are connected to that carbon?
It does. So if we're looking at primary, these are the primary hydrogens. So there's 1 carbon connected to that, but there's 3 total primary hydrogens. So what we're doing now in terms of, we have 4 unique sets, we're going to classify them, and whatever number we put here should total the total number of hydrogens in the molecule.
Oh, so it's 3.
So this is 3. How many secondaries do we have total?
8.
So there's 8 total. Of those 8, how would you further separate them? And then tertiary, we have 1. So that should be, we've at this point accounted for all of the hydrogens in this molecule.
Can you show me which one was secondary?
So with the laser here, these are equivalent due to that mirror plane. So those 2 and those 2 are secondary. And then this group and that group are the same, they're secondary. So again, we're looking at the carbon itself. It's bonded to one carbon, two carbons. There's two hydrogens, so they end up being secondary. So why do we want to do that? So I would say do that for like any problem. And so now I can ask you, of the ones you've classified, if you react this molecule with bromine and light to do a free radical substitution, which hydrogen is going to get substituted and why?
The one on the tertiary carbon.
Why?
Stability.
Stability of what?
The carbon.
So you could sort of answer this two ways. Like if you had to write down a couple sentences describing why. So the reason you want to do this, primary, secondary, tertiary, these have the weakest CH bonds, right? So if you're going to homolytically cleave in terms of ranking, this is the bond that breaks first. And specifically with bromine, that's the one it's going to go after. Because the bromine free radical mechanism does not supply enough energy to go after primary or secondary, really. So bromine's going to go this way. It's going to substitute in that order. So under those conditions, let's just write out a reaction. So bromine, light. The substitution product that you would get is that. So again, that we all understand what is meant by this. The hydrogen I've just drawn in, that hydrogen is substituted for bromine. So this, you know it's free radical because you're going from something that's nonpolar to polar. You can't do SN2, that's a very poor leaving group. Now if you think a little bit further, you substituted a tertiary hydrogen, you formed a tertiary bromide. So if you wanted to substitute that bromine, which mechanism does it have to react by? It has to go by SN1 because the bromine has to ionize to give a carbocation.
So that hydrogen on the first structure before the reaction,
Yeah.
is that one of the tertiary hydrogens, or that's one of the hydrogens for that carbon? That's that fourth bond at that carbon.
This is that tertiary hydrogen. That one is that one right there. I specifically showed it because that's the one under these conditions that is substituted. So free radical bromination is more selective than chlorination. So looking at that starting material, let me ask another question. If you were to take I'm just going to redraw it down here. You take that starting material, you treat it with chlorine and light. Chlorine's much more reactive. So my question is, how many monochlorinated isomers could you get from that starting material? What's the maximum number of monochlorinated isomers? I see why you want to say that based on these initial numbers, but then you have to consider of the secondaries, there's two different types of them. So would be 1, 2, 3, 4. So let's draw those out.
Wait, if chlorine is more selective, then why can it?
No, bromine's more selective.
Oh, okay, I know.
So chlorine, when you go through the thermodynamics with the table, the chlorine mechanism produces a lot more energy that it can basically abstract any type of hydrogen.
Oh, that's that stuff we get in class. Okay, yeah.
Right. So let's just go ahead and draw these out. And we're just going to use this order that we started with here, right? So we keep everything straight. So if we substitute a primary, it's going to look like this. Substitute one of these secondaries. Now one of these secondaries. And then finally, the tertiary. So let me probe a little bit deeper. So our first approximation is 4, and we've drawn them. Do you see any other sort of concepts buried within these structures that we could further refine our answer that would lead us to more than 4 products?
Stereochemistry?
So we'll have some stereoisomers of which specific ones. Maybe I'll give them some labels so you can just, well, there's A, B, C, and D.
I would say D.
I wouldn't agree with that. So C.
Wait, yeah.
Why would A or D not be choices for stereoisomers?
Don't stereochemistry do 180?
So that's sort of in a subcontext of stereoisomers. So why not A?
Because that carbon has 2 hydrogens coming off of it.
So yeah, that has 2 hydrogens, and then there's a mirror plane.
Mm-hmm.
So similar with A, D is not either, because that definitely has a mirror plane. So you said what?
C.
So of C, how many stereogenic carbons do you see there?
Yeah.
What'd you say?
You said 2.
2? Does everyone see 2? So I'll put those here.
I have a question.
Yeah.
In this whole problem that we just started doing, is the objective to find which one doesn't have a mirror plane or which one?
So right now we're just sort of sussing out what are all the possibilities. And so of A and D, we can say that these do not have chirality centers or stereogenic carbons because none of the carbons have 4 different substituents. So the mirror plane thing won't necessarily, in terms of like a meso definition, won't really show up in any of these.
So it's really more about the substitution.
Yeah, that's what we're looking at. So of C, if you have 2 stereogenic carbons, what's the total number of stereoisomers you could have for C? 4. So again, we're going to use that 2 to the n. So n equals 2 here. So I'm going to further dig down into this problem. Of the 4 stereoisomers, what are their relationships to one another? I want you to use the terms that we've used in lecture.
Are you talking about like NH9 and diaster?
Yes. If you had to describe to me, using like the CIP nomenclature, all of the possibilities, what could they be?
mean like from an RS standpoint?
Yeah. So what would they be? If there's 4 of them, what are all 4?
RRSS.
So we have RR, and its enantiomer SS, and then what? And its enantiomer SR. So what I'll do in green here, those are the 2 enantiomeric pairs. So then every other relationship is a diastereomer. And so I think you'll see that same relationship if you considered B as well. That's going to have 2 stereogenic carbons. So overall, I think we initially, our first approximation was 4. Our final second approximation would be 10. So that really sort of indicates to you that under these conditions, with this substrate, doing a radical chlorination would be a pretty messy endeavor. Does that spark any further questions you guys might have?
I don't know what the R to the S is or the R is to the S R. But I know what R and S are, but what I don't know here.
So when you have, so for example, this carbon bearing the 4 different substituents, that carbon can be R. This other carbon can be R as well. So that's 1 molecule. Its enantiomer would be the SS. So this carbon could be R, that carbon could be S. So that's this. And its enantiomer would be the opposite, SR. So really what you would want to do to prove to yourself what those things are is to draw each of those out with wedges and dashes. So those are the type of things you can do. Really, you don't need a textbook so much. You just kind of like do it when you have free time just to prove to yourself that you're fluent in the concept.
So why would B not the correct answer, being the fact that if you had stereogenic carbons on it?
Say that again?
Why was B not the answer? Because you just...
No, B is another answer.
Oh, okay.
So if A and D are only compounds themselves, B and C each have 4. So total, you would get 10 compounds out of this. That raise any questions? I can put up some substitution reactions. Have you guys predict the products? Okay, why don't we'll go ahead and do that. So again, a multiple choice exam. The correct answer is on the paper in front of you. What your job is apply chemical logic to, in one sense, remove distractors, while at the same time figuring out what the right answer is. So you can think of it maybe one way without looking at the answers first, just sort of answering the question, see if you can come up with that way. And then see which one, if it matches what you got. So let's I'm going to tell you this is an SN2 reaction. And so we're going to react this molecule with this molecule in the presence of a solvent, and I'm going to call that DMF. There's the structure of it. So in the prior screencast from last night, I sort of walked through what the solvents are for each mechanism. So this reaction is proceeding through SN2. So that's nucleophilic substitution bimolecular. Maybe I'll throw in some letters here. I'll call this A, call this B. Between A and B, which one is the nucleophile, which one's the electrophile? So B is the electrophile. So we have this bromine, it's delta minus, this carbon's delta plus. So by default, A is then the nucleophile. So the nucleophile supplies the electrons. So it's going to be the sulfur atom, which is negative. That's going to attack the carbon bearing the leaving group, which is the delta positive one. So the arrow starts at sulfur, the lone pair. It's attacking the carbon bearing the leaving group. And so we're using that double-headed arrow now, again. So that shows the movement of 2 electrons.
So whenever a bond breaks, that is automatically 2 electrons, right?
Yeah, so if you recall from the Lewis dot rules, you still have to obey those. So if you're forming a bond has to break, because otherwise you're gonna be violating some valency issue.
Then delta positive is above the arrow. That's above B.
Yeah.
Not above the R, but that is connected to that carbon that's in the middle, right?
Yeah. So what
By
the
default.
the delta positive is showing you is,
Out of them two, that was more positive.
yeah, of this bond, the bromine sort of owns more of those electrons. So that's why this arrow points towards bromine. It's able to accommodate that extra lone pair. So I did one of these last night, but I'll do another one just to show that you can use different conventions to think about these things as well. So we have an alkyl bromide plus sodium cyanide and acetone. Why don't you tell me what the name of that alkyl bromide is? Yeah.
Why did the DR become a part of the pipe? Why did it break off from the structure so it could join the
Here.
Yeah, like for the product.
So the electrons in this bond leave with the bromine to become bromide. So this extra lone pair gives the bromine the negative charge. That's the leaving group. The sodium counterion, see how it's still just satisfying this negative charge here. Then in the product, it's satisfying the negative charge of the bromide. So So the sodium's the counter ion, and the bromine's the leaving group. So what do you think the name of this is? So if this was a short answer test, and this was worth, if just that alone was worth 2 points, I would give you 1 point. Correct. So you've partially named it. We haven't fully named it. Because you got to remember, even though it's sort of duplicitous, right? It looks pretty simple, but there is stereochemistry with this Fisher projection. So let's go through it. We have a claim that it's R. So the stereogenic carbon, bromine's going to get the 1, hydrogen's the 4. Now the 2 groups bonded to that are both carbon, but you have a methyl versus an ethyl. So this will be 2, this will be 3. So we have a claim that it's R. We have an S. Anyone else? Who's the tiebreaker?
Yes.
S. So I think it's S as well. So these are definitely tricky because this hydrogen's coming out towards you, right? So is the bromine. So what you have to do is, if you go sort of this way, that's how you would get R, right? But since that hydrogen's coming out towards you, you have to reverse what you come up with. It's tough if your mind is in just like 2 dimensions.
Well, like, I'm looking at it like hydrogen and bromine are coming at me,
Yes.
so then the other 2 are going away from me. So then if I turn it, oh, okay, I see. I got the R, or I got the S, and then I forgot that I already rotated. Okay, now I figured it out.
So it's tricky.
She had already did it in her brain, you know.
I just did the extra
Right.
step that was unnecessary.
So we would put in front of this, oop, change color here.
And that's basically what all Fisher projections are.
Yeah. Generally speaking, one of these is probably going to be a hydrogen that's coming out towards you. So now what we want to do is, like we said, this is an SN2 reaction. For these reasons down here, the same concept. It's a bromobutane is just drawn different. This is our nucleophile, that's the counter ion, forming the same inorganic byproduct. So now this is attacking that carbon. You can leave the main chain of the Fisher projection alone.
On the left, it would be C.
So yeah, let's put in the horizontal bond. So on the left is going to be the cyanide. And on the right is the hydrogen.
And that right there is what we're dealing with. 180.
Yeah, so this is the reason that hydrogen appears to flip over to the other side is due to the mechanism of the SN2.
And that's like it attacking from the back. And then
Right. So that's how you depict it in a Fisher projection.
I hope it be a question like this, because I really understand it.
okay, I haven't watched the screencast from yesterday, but the solvent the reaction, right?
The solvent, for an SN2, not so much. What it is there to do is, remember when we're going through that reaction coordinate and you go up to a transition state?
Mm-hmm.
It's helping to stabilize that. So for this specific example, I guess I can draw it out.
So acetone just helps keep it like stable so it can get to that final form.
Right. So your nucleophiles have thus far consisted of a cation and an anion. The reason you want a polar aprotic solvent is that that solvent is going to solvate the cation. And so what do I mean by that? So this is the structure of acetone. It's 2-propanone. So it's forming this, I guess, lone pair ion interaction. And I'm just going to sort of draw that a couple times. So if the solvent is solvating that cation, that means the anion is not so much explicitly bound to this cation anymore. It's more like free floating. So it's able to do the SN2 a lot faster. So the solvents, they dissolve things and they facilitate the rate of the reaction. So I think we can name this product. There's a ambiguity last night about having a nitrile, but I think we can name this one. So why don't we see if we can name this compound. The way you would name this, maybe what I'll do with the green marker, I'm just going to number the longest chain. It's 1, 2, 3, 4. So this would be a butane nitrile. We have a substituent at the 2 position, so 2-methyl. And the 2 position is a chirality center, so we need to figure out if it's R or S.
So it being a carbon chain of 4, what did that do to the name?
So that makes it a butane. And the main parent is a cyano group, which is also called a nitrile. So it's a butane nitrile. Yeah, and at carbon 2, there's a methyl. So we still need to figure out what the stereogenic carbon at 2 is.
You saying like R is?
Yes.
Let's say R.
I agree with R as well.
Yes, R, because it would be S if all of the way it would be R.
So R 2-methyl butane nitrile. questions?
You do one of SN1 where the solvent affects what's going on?
Sure. Great.
Just really praying get these tastes in my brain just be like.
So again, the way that I introduce this material to you is it's such a way that to minimize confusion, because there's substitution, which is bimolecular and unimolecular. Then there's elimination, which is bimolecular and unimolecular. And the way your textbooks often present it is sort of like all at once. And it can be really confusing to diagnose what's important in these things. So other than me just telling you this is going to go by SN1, what are you looking for? In this case, you have a carbon-bromine bond. That's the polar bond. So you've identified that. That's the bromine's the best leading group. How do we know it's SN1? What's the classification of this bromine? So carbon bearing the bromine is what classification? It's tertiary. So that's how you're sort of, if you're thinking about like a flow chart, whether you go SN1 or SN2. So if it's tertiary, it's always going to be SN1. So let's capture that piece of information. So that bromine is going to get substituted, and the only other thing there is solvent. So now pay attention, this solvent is polar, it's ethanol, and it's protic. That's what we mean OH, that's the protic part. So it's a nucleophile, but it's not like the nucleophile you saw in SN2, where there was a cation and an anion. So this nucleophile is neutral. So what you're substituting is bromine for this oxygen and the rest of this stuff, whatever's hanging off there. So let me draw that product, and then we can consider how it gets there.
So not the hydrogen.
No. The hydrogen does not come along because you would end up with a molecule that has a plus charge on it. So this would be the major organic product. And so what main functional group is that? What?
Oh, yeah.
Let's hear it. Yeah.
I didn't want to say it.
I don't know. I was
As
like,
far
that's
as
what I said, yes.
So other factors that you're looking for SN1, you definitely need a tertiary substrate. The nucleophile is going to be something neutral. It's typically a polar protic solvent.
So can protic be interchanged with neutral as far as like description?
I don't really want to use the word interchange because they're sort of separate things. They're not really interchangeable in that sense.
Can you define protic?
So really what you're looking for is, in this mechanism, an OH. This stuff hanging off there can be like anything. It can be water itself, where this would just be another H. Or you could have one methyl, or you could have, you just have one carbon, so it would be methanol. You could have a branching carbon, isopropanol, just.
So protic is just an alcohol? In our case?
In your case, yeah. In general, what are other protic things like amines? NH. carboxylic acids have an OH. Those are protic things.
So they're functional groups with an OH.
Yes. So what could be another, say you didn't want to use ethanol. Say you wanted to use formic acid. So that's a polar protic solvent, formic acid. So what would this product be?
It would be
Again, you're substituting that bromine.
so only one of the H's would not come.
Yeah, typically the hydrogen bonded to the heteroatom is not incorporated into the final product.
Oh, wait, okay.
So this would be an ester. So keep in mind the big picture of this for this module. It's substitution. So you're substituting bromine for this entire group. So you're making a new functional group. So the mechanisms you've learned to do substitution are free radical SN2 and SN1. So in the next module, so you would know, let me just draw it on here so you see why everything's connected and why you really can't forget stuff. Because it builds upon itself. So there's that substrate, and you think to yourself, how would I make that? So what do I need to put here? You've already identified this is a tertiary bromide. So how do you arrive at that? A substitution of a tertiary hydrogen. So your starting material for that would be that, right? And you've seen this from radical chemistry. So that's an H to Br substitution. And you just saw above how to do SN1 chemistry on that. But say you weren't treating with something neutral. And again, this isn't going to be on the exam tomorrow, but it's where we're going. And this is why I sort of segregate these topics. You have a tertiary bromide. Now this is not neutral. You have a cation and an anion. You know it can't do SN2. So what does it do? It does a different mechanism called elimination. So you identify the leaving group, you have to go one carbon out. That carbon has, doesn't matter which one because they're all the same, that has a hydrogen. This will now, instead of acting as a nucleophile, it acts as a base. It abstracts a hydrogen and eliminates that bromine. So what do you end up with in that case? So an alkene. So you've taken an alkane, you've made an alkyl bromide, now you've made an alkene. So that's going to be like chapter 8. Then chapter 9, we're going to use an alkene as a nucleophile. It's a source of electrons that can react with an electrophile. So we're basically looking at something that's just CCCH bonds, and we're going to make it something more complex. So this is where in learning organic, you move you move beyond just learning reactions, but like a strategy. So do any of you play chess? So you know the rules of chess. So there's like individual rules, right? Like a piece can do this. So that's sort of useful, you know how to play. But if you really want to get good, you have to get like a strategy, right? I'm going to do this, then this, and ultimately you're trying to get the other opponent at a checkmate. And so synthesis is a strategy of that. Like this is sort of one thing, two thing, and you're ultimately building towards something complex that we can use as humans. We want some use from it. And then sort of near, I guess, the end of this month, since the semester is coming to a close, you're going to learn to run reactions this way, but ultimately I'll show you how to think. If you're given a final product, how do you think backwards to get to something like this?
And that's the final, basically?
That's where we're headed. So look at this wall. This wall is part of a building, right? So the building has a shape, it has a form. The molecules I'll show you, like the molecule of the lecture, it has like a shape, has a form. So you sort of see how this is put together. You're going to like eventually see how those molecules are put together by running these reactions in a certain sequence.
Okay, so in this dialog reaction, I see how, because the solvent isn't neutral, that the oxygen will attack the carbons, the hydrogen that's connected to the carbon out, one carbon out from the stereogenic carbon. But I don't see how it became a double bond, and I don't see how it would be like CH3, and then
This OH.
yeah.
So again, this is the stuff you'll do in the next module. So I'm not going to go too much into it tonight, just because I don't want to like overwhelm you with stuff that's not going to be on the exam. But it's a different mechanism. So right now you've learned 3 mechanisms: the free radical substitution, SN1, SN2. So just keep in mind that you're in it to win it here, and
Learn is a strong word.
it's a bold statement.
So if it has an alcohol part of the solvent, that would make it neutral? Or would that's just...
Ultimately, in general, anything you propose as a product has to be neutral, meaning you can't really have formal charges on things, because that's not how compounds are isolated in reality. Let me put up some comparison problems and see how you're thinking about them.
I know one day in class we went over something and you said that it went all the way back to K8.
Yep.
I don't know what that was.
Isn't that like Boolean or something?
Yeah, we can do one of those. So if you were given these 2 substrates in any nucleophile, which one would react faster by SN2? So we'll write some A or B. How do you classify both of these?
I say it would be B. I don't know
the primary, secondary, tertiary.
They're both secondary.
They're both secondary alkyl bromides. So there's a big difference between one of them, and how would you describe that difference?
sp2 carbons.
So yeah, the presence of the alkene in B makes that secondary allylic. So that one's going to react faster. That allylic bond helps that leaving group leave.
So like a double bond would make it more stable, so the leaving group could leave without changing too much.
Right.
Does that have something to do with the fact that it will be easier for it to be stable whenever something leaves?
Yeah, so it's sort of a way you could think about this. If we were drawing a resonance form, that's sort of a ridiculous resonance form because you've like completely cleaved that carbon-bromine bond, but it does help to sort of rationalize why B is going to be faster. So getting back to the other comment that was made, say you had this versus that. So which one of those would be faster and why?
You said which would be faster?
Yeah, if you were doing SN2.
I say D.
So D is going to be faster than C.
Because it's more
So,
negative.
well, the reason you want to use is if you're comparing the pKa's of the conjugate acids of these things, you have HF versus HBr. And so,
HF is way more.
Actually the HBr is going to be much more acidic than the HF. So its conjugate base is much more stable. So D is going to react faster. So bromine is better than fluorine for leaving group ability. So this next one,
Is it gonna be like compare rate questions on
yeah, there's a couple questions like this where you have to consider different substrates. So you have these two chlorides. And again, the question we're asking is which one's going to react the fastest and why? we'll see ya.
I'll say F.
So what's your reason?
It's closer to the end, so it'd be easier to break. Cause, I mean, E is in the middle of the whole molecule, so that means you would have to like go more.
So we're getting there. They're both secondary, right?
Yeah.
So you can't discriminate amongst that criteria. So we're getting to what the right answer is. This being closer to the end of the chain means it's less hindered. You see how this chlorine is closer to this like branching point?
Mhm.
So I'm going to do something over here on this part of the screen to show you, hopefully, why you see this reacts faster than that. Because if it's doing SN2, remember it has to attack 180 degrees from the leaving group.
Doesn't it like take up more space?
Yeah, so this group is much bigger. So I'm going to do a Newman projection looking down the carbon-chlorine bond. So maybe bear with me as I present this because it might not be obvious to you what I'm doing. For E, we're going to look down that bond. So we're looking down the carbon-chlorine bond, so you're not going to see, maybe what I'll do for the chlorine is since this has 3 lone pairs, I'll show those in the Newman projection. So the chlorine's in the back. So off to one side here we have hydrogen, we have an ethyl group, and then we have this tert-butyl group. So again, this is directly looking at if the nucleophile was towards you, attacking that carbon, and then the chlorine in front leaving.
I don't see how the F3 are chlorine.
Those are the lone pairs coming off the chlorine. So these 3 lone pairs. So if we do this for the other one, we have a methyl. We have, well, I'll sort of keep maybe then hydrogen, then methyl. So it's not the best representation of this, but you can see the carbon that's being attacked. This group right here is really hindering that sigma star orbital more so than when you have this CH2 spacer between it.
I have a question. That hydrogen is coming from the area where the arrow is marked.
Yeah, so this carbon has 1 hydrogen.
Yeah. And then
This
that
carbon has 1 hydrogen.
Can we go back to that second projection? Because I was still writing first.
This one. So if we're looking down this bond, this CH2 is right there. And then this like chicken foot looking thing is right there. So that methyl group is the end. Maybe I'll, yeah.
The placement of that structure on this last one, why would it not be on the side if you're looking at it from like, from L?
Oh, I didn't sort of draw these corresponding to
Oh,
any
okay.
particular like rotation or anything. Maybe let me ask you a challenge. Oh boy. you think you could draw a mechanism for how this happens? Without, I'm pretty sure you could. But what I want to say first is, when you draw a mechanism to go from A to B, you really need to think about like what is changing from A going to B. If you have a list of like things you have to do, then those translate into the arrows that you have to push. And so really right now what you're doing is just making observations. What's the first thing that pops into your mind going from the starting material to the product?
Another carbon.
What, just putting a roof on it? You said another carbon.
Well, I mean, it's not another carbon, it's just moving.
So the ring has enlarged. So maybe what I'll do, I'm going to put a 4 in here and a 5 in there. So what else has changed?
Cl substituted for an OH.
So those are two main things I think we can get started with. And what you want to do is, I think, use numbering to sort of track the atoms. Again, this has nothing to do with like the formal name. It's just mapping where each atom is ending up. So I'm going to call this 1, 2, 3, 4, 5, 6. So I'm going to number this like the correct way, because I don't want to like show both and like cause any confusion. So the methyl group is obviously going to be 1, then we go to 2, so I'm going to go up, call this 3, 4, 5, 6. So now what we can further do over in our sort of observations here is that we are depending on how you look at it, so I'm gonna phrase this one way. We're forming a bond between carbon 6 and carbon 2. Because the molecule is sort of symmetric, you could also view it as 4 going to 2. Either way you do it, you're going to get the same thing. So we have a secondary alkyl chloride in the presence of water, which is a polar protic solvent. There's no strong nucleophile, so we're going to invoke an SN1 mechanism here. So even though it's secondary, they can still go through SN1.
Then you said polar protic?
Yeah. So yeah, water is polar protic. So we're going to have, we know that chlorine has to leave. We said we're starting with a secondary chloride. We get a secondary carbocation. We're looking at the carbon bearing the leaving group that ionized. So carbon 2, I want to call that the alpha carbon. And the carbons bonded to it, I'm going to call beta and beta prime because they're both different. So you may think what I'm about to say that I was lying to you in class. when you look at beta and beta prime, you're looking for a rearrangement to happen to a more stable carbocation. This beta prime has a hydrogen here, right? If that hydrogen moved over, you would end up with a tertiary carbocation. But it's still in a four-membered ring, and we know that there's some ring strain.
So they go back to again?
Yeah, please. Say it one more time.
So let me draw that out so you guys can sort of follow. I'm just going to show you both pathways this can go so that you sort of appreciate the complexity, I guess. So maybe I'll sort of draw it. So say the hydrogen at the beta carbon migrated. Oop. That would leave you with this, right? Which is primary. So we know that that route's no good. So say your other choice is now this beta prime hydrogen is going to migrate over.
Which hydrogen is moving?
It's this one right here at the beta prime carbon. It's migrating over one carbon.
So why would that carbon that is migrating to not already have something?
Because it's only starting with one.
Oh.
It's just starting with I haven't drawn it, but it's starting with just one there.
Oh, I see now.
So when you go down and then this way, you go from secondary to tertiary, which you think is good. But in this sense, keep in mind, you're already given where you have to go.
Mm-hmm.
So that's why you think, well, this should be good, but it's not. And the reason it's not is because you're still keeping that four-membered ring. So instead of this hydrogen moving over, this carbon-carbon bond actually moves over. So when it does that, the ring gets larger, but you're still maintaining a secondary carbocation. And the reason you can go from secondary to secondary is you're relieving this ring strain. So that's the overriding factor in this mechanism. So I'm going to call this C6 to C2. So this whole bond will come over, and I'm going to draw it without moving too much stuff first. Blue, 1, 2. So I've migrated C6 to C2, so the plus charge ends up at C3. Now what you see is the ring has grown. And so this is actually equivalent to this. Now the nucleophile water then comes in to attack that.
When we classified the beta and beta prime for the bottom two, we classified them as primary and tertiary. You were talking about from the location of the.
So right here I'm talking about the carbocation itself.
Okay.
So you can do these so-called degenerate secondary to secondary if you're gaining something in the process. And really what you're gaining in this sense is more stability through a larger ring. So I just wanted to show you this example because if you were not given this product, you would most likely go this route to that.
So just because of your solvent, it would rather move a bond over moving a hydrogen?
So that and the fact that, you know, if you consider what this bond angle is, 90 degrees, with this bond moving over, you're now getting into a normal sp3 hybridized bond angle. So that relieves quite a bit of strain. So I think we have time for one more question.
So for beta prime and the beta, which one would be better?
So in this reaction, the beta carbon, the beta prime, is going to be better in terms of when it opens that ring up. You go from 4 to 5.
The tertiary carbon. The tertiary carbon.
Well, instead of, so if you look at this, you have 1 path, 2 paths, 3 paths.
Oh, that's the whole thing.
Right. So these are sort of more advanced problems, just to give you an idea that when if you're in the habit of like solving problems on your own, you want to explore all your choices before you make a final decision. Because like if you're just considering this, then you're sort of missing these other things.
So under what circumstance would it want to go that tertiary pathway?
There might be, I'm sure there could be like solvents or temperatures that you could use to control it, to funnel it into that pathway. So a lot of this, we draw these arrows, but the way chemists think about these are, if you're like, if you can imagine like a hilly landscape, and there's like a giant ball, you're at the top, and you roll it down, you know, this is sort of like one surface it can roll down. This is another surface. So you can manipulate which way that ball goes based on the conditions the reagents are subjected to. Maybe let me just show you one more thing and then we'll wrap up, just so you can see where this is going. So this one is going to be, it's going to have a symmetry element, so it makes it more straightforward to think about. Say you were given the task of synthesizing this molecule. Knowing everything you know now, you could do that. Probably what you don't know how to think about is sort of the reverse direction. So you have to make that. So you make it from what? So this is like reverse engineering in a way. If you recognize that this group here is a nitrile that can come from a cyanide, that you're going to make that bond. So the arrow that we use to think sort of in the reverse direction is this arrow here. If we want to make that, we know we can get cyanide into a molecule by doing an SN2 reaction. And so how do we get that bromine there? We know that we can do a CH substitution. With bromine and light. So this sequence is sort of straightforward in the sense that when you're thinking backwards, there's really only one functional group you have to worry about. You can get that in there through SN2. You get that in there through radical substitution. This molecule can only give you one bromine substitution product. So I think over the past couple weeks, we've come a long way in the sense of like learning concepts and reactions. And now, especially in the next module, we're going to get into not only understanding the mechanisms of them, but applying them in these sequences. So it gets back to that sort of chess strategy. So I'll upload this onto YouTube if you want to watch it again. You lived it, so I don't know if you want to watch it. The one from last night is up there. If you have any burning questions, you can send me an email tonight. I'll try to respond as soon as I can. And obviously your exam is tomorrow.